Hello, we will see 5 levels of proof in this video. At the end of each proof, I will explain a key concept about it. But first we have to tackle the question, why? Why prove? The answer is that there are many patterns in the world of math. But sometimes they can turn out to be deceptive. They seem like a pattern when they are actually not. A proposition that seems intuitive but is not proven yet is called a conjecture. Take Moser's circle, for instance. As you can see, the pattern breaks. At first it seems the number of areas is multiplying itself by 2, but then the pattern suddenly breaks when the number of points is 6. You can make more research on why it happened after this video, and those sudden unexpected pattern breaks happen in a lot of math conjectures. This is why it's important to prove, so that we differentiate between what's a fabrication of our minds and what is the truth. Now let us begin at level 1. By the way, I encourage you to pause the video at each problem and try to solve when this icon appears. Take 3 consecutive real numbers. Prove that the smallest and largest numbers are factors of the number preceding the square of the second number. Alright, to solve this problem, we have to use something called abstraction. While it is good to replace in numbers to understand what we're asked to prove and to give the problem a sanity check, this ultimately amounts to nothing except for gaining understanding. So instead we'll use abstraction, which means that we will get rid of any detail that's irrelevant. For instance, what specific numbers we're working with is irrelevant, so we'll replace them with variables. The only relevant detail is their consecutive, so we'll label them n, n plus 1, n plus 2. Now we will express the product of the largest and smallest number, which are n plus 2 and n, like this. We label the equality a. Now we will express the number preceding the square of n plus 1, which is... All I did up to now is expansion and simplification. From the equalities, a and b, we deduce that the largest and smallest of the 3 consecutive numbers are the factors of the number preceding the square of the second number. And just like that, our proof is complete. So the takeaway here is that you should always use abstraction to make your proof more general, then find a way to express a relationship between the numbers if the problem is simple enough. By the way, this is a very direct proof, also called construction proof. Level 2. Assume that n is a positive non-zero integer. Prove that if one selects any different n plus 1 numbers from the set 1, 2, 3 up to 2n, then at least 2 of the selected numbers will sum to 2n plus 1. In order to prove this, we will use a strong tool called the pigeonhole principle. I will first explain what it is. Imagine 4 pigeons and 3 boxes. We want to put all pigeons inside the boxes. There must be at the very least 2 pigeons in the same box. The pigeons could be rearranged differently so that all 4 are in the same box, but no matter what arrangement we use, it is guaranteed that one box has at least 2 pigeons. If there were 7 pigeons in 3 boxes, then at least one box would contain 3 pigeons. Try to imagine splitting the pigeons as evenly as possible among the given boxes, then counting in the box with most pigeons. This may sound trivial or unrelated to the proof, but when we change what a box is and what the pigeons are, this suddenly becomes an extremely powerful tool. Here, let the boxes be every addition pair that sums to 2n plus 1, from the set 1, 2, 3 to n, n plus 1, to 2n minus 2, 2n minus 1, 2n. Notice that every 2 symmetrical numbers with respect to n and n plus 1 sum up to 2n plus 1. This is because of 2 things. First, because the numbers are increasing and decreasing by 1, effectively canceling the change when summed, leaving only 2n plus 1 as their sum. And because the set contains 2n elements, which is an even number, when we pair each 2 number of the set, we'll have half of the number of elements as addition pairs, meaning there are very exactly n possible addition pairs, which are 1 plus 2n, 2 plus 2n minus 1, 3 plus 2n minus 2, until n plus 1. Imagine those as our boxes. When we pick n plus 1 elements, pigeonhole principle will suddenly occur, and you will quickly realize what happens if you imagine the pairs as boxes. If every element spreads evenly among the n boxes, there will still be one element left, which will fill a box already containing a number, giving us at the very least one box containing two elements, which means one addition pair that sums to 2n plus 1. So according to the pigeonhole principle, there must exist at least one addition that sums to 2n plus 1 when picking n plus 1 elements from a set with 2n elements, which completes our proof. Note, the pairs adding up to 2n plus 1 isn't constant. This proof shows that the sum of the first and last elements of a set with 2n elements exists when picking n plus 1 elements from it. The takeaway of this problem is the pigeonhole principle. This is very useful to prove the existence of a specific thing. All it requires is to understand what are the elements and the boxes to use. I would also like to mention that there are two types of proofs: proving that a statement is true for all numbers, or proving that an element exists. Pigeonhole principle is very good for the latter. Level 3. Prove that the square root of 2 is not a rational number. You could say since 2 is not a perfect square, then its square root is obviously irrational. But that's actually wrong and flawed, because you just proved something by assuming it, which is not rigorous at all. Instead, we need to make a proof by contradiction, as it is the easiest way to prove the absence of a property. To make it work, we start by assuming the complement of what we want to prove. Then we reach an obviously wrong result. This will, by contradiction, prove that the complement was wrong. Thus, the complement of the complement, which is the original statement, will be true. But first, what is the complement of a statement? Well, it is the logical negation of that statement. We denote it with a tilde. In order to get the complement of a statement, we add not, then remove our statement from all the possibilities. Once again, note that it's extremely important to not just take the opposite of the statement, but instead remove it from the possibilities. Alternatively, if the original statement has a not in it, we simply remove it, which is what we're going to do right now. Suppose the square root of 2 is a rational number. This means we can write it as the fraction p over q, such that p and q are co-prime positive integers, meaning that the fraction is in its simplest possible form and there are no common factors. We will now square the fraction and the square root of 2. Then rearrange the equation to get 2q squared equals p squared. Thus, p squared is an even number. But what does that tell us about p? Well, we can prove that if p squared is even, then so is p. To do that, we'll use a proof by contrapositive, also known as indirect proof. To do it, we need to prove that the complement of the result leads to the complement of the original condition. Note that it is extremely important to go that way. P is an integer. Thus, it can be either even or odd. There are only two possibilities. We'll make the complement of the statements with that in mind. The original result is p is an even number, so its complement is p is not an even number. And because it can only be either odd or even, this must mean the complement of the result is that p is an odd number. The condition is p squared is even. Its complement is p squared is an odd number. As I previously said, when proving by contrapositive, we must go in the opposite way, so from result complement to condition complement. This is extremely useful to swap between the result and condition when you realize that it's easier to prove from the result. Anyways, we start by assuming p is odd. Thus it can be written as 2n plus 1. We will now square it and rearrange the terms after using binomial expansion. Notice that I've written p squared in the form 2a plus 1, meaning p squared must be an odd number if p is odd. This proves by contrapositive that if p squared is even, then p is also even. P is even because p squared is even, so we can replace it with 2k instead. We expand, then divide both sides by 2 to find that q squared equals 2k squared. Thus, q squared is even, which means that q is even for the same contrapositive proof I previously explained. Because of that, q can be expressed as 2k prime, and as you can see, 2 is a common factor between q and p, which contradicts that p and q are co-prime. So our initial assumption that the square root of 2 is rational was wrong. This proves by contradiction that the square root of 2 is not a rational number. I would like to mention that the step of proving that both numbers are even doesn't generalize when you change what's inside the square root, but it's also the only step that changes. You will always reach the same contradiction that p and q are not co-prime when trying to prove that the square root of a number is not rational. The takeaway of this problem is that there are two other ways to prove, by contrapositive and by contradiction. Both involve using the complement of a statement in different ways. Proof by contrapositive is about taking the complement of the result, then proving it leads to the complement of the condition, in order to prove that the condition leads to the result. Then there is proof by contradiction, which uses the complement of the whole statement to not reach the desired result, but instead a contradiction, meaning that the original statement was true. Level 4. Prove that the sum of the first n odd natural numbers equals n square, such that n is a non-zero natural number. What follows is not a solution, but a geometrical visualization to represent the proof and allow you to grasp the problem. Check this animation. As you can see, the numbers up to 7 are getting squared. Then the squares get split so that the units that made each new square are grouped. We realize by that groupment that our squares were actually made up of the sum of the first odd numbers, and with each additional odd number, an additional square. I hope that visualization was intuitive, but there is a problem with this geometrical proof. The fact that it is actually not rigorous enough because unlike the n terms, it doesn't go to infinity. I animated a very limited numbers of squares, and we want to prove for every single n, not just the 7 first ones. So instead, we'll use a proof by induction. If you're familiar with sequences, you already know where this is going. In fact, we'll also solve it by using an arithmetic series later. To prove by induction, we can follow these steps. First, prove that it works for the basic case, meaning that our statement is true with the smallest value of n. Second, suppose that what we want to prove is true with n terms. Then prove from the supposition that the statement is true for n plus 1. If we can follow these steps, we would have proved by induction whatever we want to. Let's practice them with this problem. The basic case would be with n equals 1, so we have only the first odd number, which is 1, and 1 is clearly equal to 1 square. So the basic case is true. We make an assumption that for n terms, 1 plus 3 plus 5 plus 7, until plus 2n minus 1 equals n square, such that 2n minus 1 is the term number n. Note that I expressed it as 2n minus 1 and not 2n plus 1, because I want n, the number of added terms, to start with 1 and not 0, so that it'll make our proof more easier to work with and be consistent with our base case and the problem specifying non-zero n. Now, can we prove that if it's true with n terms, then it's true with n plus 1 terms? Let's see. We clearly know that the difference between each consecutive odd numbers is 2, so we can express the n plus 1 term as the n term plus 2, which is 2n minus 1 plus 2. It's equal to 2n plus 1. We will then express the sum, 1 plus 3 plus 5 plus 7 until plus 2n minus 1 plus 2n plus 1. From what we previously supposed, we can replace the sum up to the n term with n square, so we get n square plus 2, n plus 1, and according to binomial expansion, this is n plus 1 square. So, when we assume the sum of the first n odd terms, we get n square. When we assume the sum of the first n plus 1 odd terms, we get n plus 1 square. Thus, our base case is true. And when our statement is true for n, it becomes true for n plus 1. This proves by induction that the sum of the first n odd terms is always n square. Furthermore, we can use sequences. Watch. Because of the way un is structured, we know it's an arithmetic sequence. So when we calculate the sum of its terms up to n, we get Sn is equal to the number of terms, which is n divided by 2 times u1 plus un, which we previously wrote. After we calculate it and simplify, we find that the sum of the arithmetic series is n square. This is maybe less rigorous than what we did before, because it relies on how arithmetic series work, something we haven't proved. But we can appreciate this proof regardless. So the takeaway is proof by induction. It works this way. We start by laying the base case with the lowest acceptable n term. Then we assume the proof is true for n and prove from it that the same works with n plus 1. Level 5. N is a non-zero natural number. We define the sequence a1, a2, a3 recursively where a1 equals 1, a2 equals 4. And when n is greater than or equal to 3, an equals 2 an minus 1 minus an minus 2 plus 2. Through scratch work, conjecture a formula for an. Then prove whether that formula is wrong or right. First, let's try to come up with A3, A4, and A5 by using the recursive definition. The more terms we come up with, the less likely it is we make an error. As we can see, A1, A2, A3, A4, A5 are 1, 4, 9, 16, 25. Each term is seemingly getting squared. This is why I can conjecture that AN equals N square. Now let's prove whether it's true or false. In order to do so, we will use strong induction to see whether my conjecture was right or flawed. If I fail to make the proof and find a contradiction despite using the actual statement, that would mean that my conjecture was wrong. Otherwise, the conjecture is true. Strong induction is just like induction, but there can be more than one base cases, and you don't just assume something with the N term to be true. Instead, you assume everything up to the N term being true. This can provide much more information for us to make a proof. Let's try this. We start with 2 base cases instead of 1, because the AN expression that was given by the exercise doesn't contain N equals 2, so we have to account for it here. A1 equals 1 square, which is 1, as stated before. A2 equals 2 square, which is 4, as stated before. So our base cases are true. Now we'll suppose that AN equals N square, and for every term before AN, this is true. We will now replace the term AN of the given recursive expression when N is greater than or equal to 3, while making the necessary changes for it to work with AN plus 1. Thanks to our induction hypothesis, we know that AN is N square, but we also know thanks to the strong induction that AN minus 1 is N minus 1 square, so we replace them. We expand and simplify. Since our base cases are true, and for AN and every term before it to equal N square, we find AN plus 1 equals N plus 1 square, we can conclude by strong induction that our assumption was right. For every number N, we find AN equals N square. And just like that, our proof is completed and the conjecture was right. The takeaway of this problem is that another way of proving is strong induction, but you'll rarely need to use it instead of induction. This technique is extremely powerful and can allow you very easily to prove a lot of things rigorously. However, you must be very careful while using it to define as many base cases as necessary, or else you'll be able to reach disastrous proofs. For one tiny mistake can ruin all of your induction. So be careful. Before I finish this video, I would like to appreciate this problem since it actually feels a lot like doing a mathematician work. Starting with an observation about some numbers or elements, conjecturing a formula or a theorem, then proving it. Thank you for watching this video. It is from a series I'm currently working on called The Art of Math, with a slightly different format than usual. I think I may change format as I did here, once every 3 or 4 episodes to keep it fresh. You can like the video to support me and check the other videos I've made. Take care.